How in general do we compute the state transition matrix? This is an important question because this will affect a number of things that we'll be looking at in terms of the solution of our systems. So there are three different methods for computing functions of a square matrix. There's the transform method, spectral mapping theorem, and the Cayley-Hamilton theorem. We'll look briefly at each of these. Okay, so the first case is we wish to compute a to the power k. So this is solution by transform. And here, again, we're looking at a discrete time problem, and so it is appropriate to use a discrete time transform, either the z transform or the q transform. What's the difference between the z transform and the q transform? The z transform is your standard z transform. Q transform is related to the variable q is actually the inverse of z to the power minus 1. And so these two are closely related. Sometimes it's more convenient to use the q transform, sometimes more convenient to use the z transform. The z is most commonly used, and so, but here I give both. And so this is the state transition matrix, or a form of it, in the discrete time. If we were to use the continuous time state transition matrix, and we'll see that when we look at this solution of the continuous time problem, we'll also end up with the state transition matrix. And in that case, the state transition matrix, instead of using the z transform or the q transform, we'll use the Laplace transform. Okay, so, but it'll be very similar. It'll be a similar kind of situation. Well, let's look at an example. Here's an example. Here's a matrix A, and if we take I minus q times A to the power minus 1, so that's this matrix with an inverse, I get all of this stuff. Okay, so I have all of these terms, and I basically need to take the inverse q transform for each of these terms. Okay, so this is our matrix we're concerned about, and we can use this result. Alpha to the power k in the time domain corresponds to 1 over 1 minus alpha q. And so here I've done a partial fraction expansion on each of the terms, and so I notice most of my terms look like this. In fact, they all look like this. So basically we're getting some constant times an expression like this. And so we can go through and term by term take the inverse q transform all the way through, and we get this expression. So this then is our state transition matrix for the system, for this particular system. So you notice it has various quantities raised to the power k. Notice here I have 1 minus q to the power, so basically it's 1 to the power k, which is just 1. So that's like a unit step where it's just constant values of 1, and so I just get constant values in some of these cases, right? So that's our state transition matrix. So that's how we would do it using transform methods. We would basically take our function, which involves a symbolic matrix inverse. We would go through and do partial fraction expansions so that we can get terms that appear like terms in a Laplace transform table or Q transform table or Z transform table, and then we take the inverse transform. Okay? You can also use MATLAB, the symbolic math toolbox. The symbolic math toolbox understands the Laplace transform and the Z transform. It doesn't do the Q transform, but it'll understand both of those transforms. So that's the first method. That's the transform method. We just go through and we get our expression in the transform. We take the inverse transform of that entire expression. The second method uses what's called the spectral mapping theorem. And so here we're going to assume a spectral or Jordan decomposition. And so it turns out that we can compute an analytic function of the matrix A by this expression. The function of A is equal to V times the function of lambda times V inverse. And so this is the trick that we're going to use in the spectral mapping theorem. Actually, there's a much more powerful version of the spectral mapping theorem because, well, anyway, so this is the method we would use. The function f of lambda, the whole reason for this is that this function is much easier to compute than the original function. Okay, so even though it requires this Jordan decomposition or eigenvalue decomposition, the whole thing ends up still being simpler. In general, however, this does not work well with defective matrices. So that is, if we actually have a Jordan form instead of a diagonal form, it doesn't work quite as well. So I'm going to look at it primarily in the diagonal form, assuming our system is in the diagonal form. So for the diagonal matrix like this, an analytic function of this matrix can be shown to be this. That is, I'm just taking the function of the diagonal elements. Okay, so that is the value of this. So what exactly do we mean by an analytic function? An analytic function is a function that can be represented by a Taylor expansion or a Maclaurin series. Okay, so any function that can be represented that way, we can do this with. In general, some other function, not. Okay, but at least with an analytic function, we can do this. So I recommend looking at some of the examples in the examples problems page to go through this. So, but that's basically what we do. Okay, so we take our matrix, we get the diagonalization of it, we get the eigenvector matrices, we form lambda to the power k, that is, we raise the elements to the power k. Actually, you can go through and show that this is lambda to the power k just by multiplying lambda by itself multiple times, and you'll get this expression. And then we go through and we multiply it out, and we get the expression a to the power k. And once we've got this expression, then we can go back and check, because remember, the state transition matrix of k minus L, a to the power k minus L, must be the identity matrix. So if we stick in 0 for our exponent, we should get the identity matrix. And so that's one way to check to see whether you've done the calculation correctly. If you don't end up with the identity matrix, that means you've done something wrong. Maybe you've dropped a sign, or you've done something. Okay, something incorrect. So that is a nice check for this. All right, using the Cayley-Hamilton theorem. So the Cayley-Hamilton theorem is a special theorem that works with square matrices. So for square matrices, we have a characteristic polynomial. The determinant of Si minus A is the characteristic polynomial, or Zi minus A if it's discrete time, if you want to use Z domain. So the determinant of that, and so that gives you a polynomial. And so in general, that will be, for an nth order system, it'll be an nth order polynomial. And so that polynomial, if we now plug in the matrix A instead of S, then this is what we get. And notice I have A here, so S plus the constant term, but notice the constant term is actually multiplied by A to the power 0, which is the identity matrix. So when we evaluate a polynomial at a matrix, we keep track of the fact that the 0 term actually is multiplied by an identity. The Cayley-Hamilton theorem basically says this: the characteristic polynomial evaluated at the matrix is equal to 0. That is, a matrix satisfies its own characteristic polynomial. That's one way of saying it. So that tells us something about the relationship between A, the powers of A, and the coefficients of the characteristic polynomial. So in particular, I can take this equation, set it equal to 0, and solve for the highest power of A, and I can write it in terms of lower powers of A. This means that any power of A greater than n can be expressed as a function of powers of A up to the n minus first power of A, any function. And so as a result, an analytic function can be expressed as a polynomial in A. As a polynomial in A. So that is astounding. It's a polynomial A of degree up to n minus 1. So regardless of the function, we can always write it as a function, as a polynomial in the matrix A. So here's our characteristic polynomial evaluated at A, the function f can be expressed as a polynomial in A. Now notice that so A is just the matrix. The coefficients of this polynomial are functions of k. So we know that the function of A, which may be a function of k, basically A itself is not a function of k, and the exponents of A are not functions of k, and so the coefficients of the polynomial are functions of k. So we have some functions g0 to gn minus 1. If we can find these functions, then we have f. Okay, so this is the trick that we use in using Cayley-Hamilton. So these functions g0 to gn minus 1 are obtained by interpolation. What exactly does that mean? So interpolation, basically it means that these two functions, g at time, so if we think of this as g of x comma k, where x is evaluated at A, then we can think of g, so that's the polynomial. This is the original function that we're looking at. So when you think of this, you can think, for example, this as being a polynomial in x. This is, let's say, e to the x, some function of x. Okay, and basically the interpolation occurs at the eigenvalues. That is, these two functions are equal to each other at the values of x that are the eigenvalues of A. So in general, for an nth order matrix, we'll have n eigenvalues. And so the function that we seek is this, f of x. In this case, the function that we seek is x to the power k. And so our function is of this form. It's the same form that we had before. Notice instead of a's here, I have x's. So again, this is a polynomial in x with coefficients g. So the overall function g and f must be equal at the eigenvalue. So this is the function that we're seeking, and so that's what goes in here. I could have some other function like e to the a, in which case this would be e to the x. Okay, but in this discrete time case, we have x to the power k. So because we're looking at this function. All right. So these two functions need to be equal to each other at the eigenvalues, and so I set them equal to each other. That is, I set this equal to this, and then I plug in the eigenvalues, lambda 1 to lambda n. And so basically this is actually a set of n equations. Those n equations I can stack into a matrix form. And so notice here I have lambdas instead of x. Okay, and so I'm going to move those to the side. Lambda 1 is equal to all of this sum, all the way down to lambda n, which is this sum. So notice this involves lambda 1, this involves lambda n. Okay, and so I've just stacked those equations into, well, in vectors, into vectors. Now this lambda, all the lambdas here, I'm sorry, these g's that appear here, it's the same g all the way down, the same g0 all the way down. And so I can factor the g's out this way, and I get this matrix. So this is equal to this matrix times this. I've basically set myself up for a linear algebra equation. This matrix is an n by n matrix. It actually has a name. It's called a vandermonde matrix. This n by n matrix now, we can show that as long as we do not have repeated eigenvalues, this matrix is non-singular. As long as lambda 1 is not equal to lambda 3 or whatever. As long as we do not have repeated eigenvalues, this, and so we kind of said that, then this matrix is going to be non-singular. In which case, I can now solve for my unknowns. I don't know what these functions are. I need to find what these functions are. If this matrix is invertible, I can solve uniquely for these functions. And so taking the inverse then, I get this expression. Notice that this matrix is independent of k. There's no k that appears in here. The k values appear here. And notice basically we get powers of lambda. Lambdas to the power k. We saw that when we looked at our example of a to the k. We saw that example we had all of these numbers to the power k. And so these are those numbers to the power k. And so this gives us the functions that we're looking for. Once we have solved this equation for the g's, then we have this expression, and we know how to compute a to the power k. So look at the examples, the sample problems, and to see how this works. Okay, so in the case that we had simple roots, simple poles, then we had the vandermonde matrix, and the vandermonde matrix was non-singular. In the event that you have repeated roots, okay, in the case of repeated roots, like when you have a Jordan form or something like that, then the interpolation, so the problem is that the interpolation, if you evaluate at repeated roots, you're evaluating at the same value. In other words, you're not getting any new equation. When you evaluate it more than once, you're not getting a new equation. You're getting the same equation appearing twice, and that's why the vandermonde matrix is singular in that case. And so instead of evaluating those repeated roots multiple times, we evaluate not just the repeated root, but also the derivative at that value. So not only must the two functions at the value be equal, but the two functions at the repeated value must also be equal. So if it's repeated r times, then we have these interpolation conditions. That is, the derivatives of g and f, the kth derivatives, evaluated at the eigenvalues must be equal. So that's what this is saying. So not only must the values be equal, but the derivatives must be equal, all the way up to r minus 1. So this is actually r terms altogether. So if it's repeated r times, this is giving us r interpolation conditions. So in general, we will have n interpolation conditions. That is associated with all the eigenvalues, including the repeated eigenvalues. This will give n equations and n unknowns. That is, the unknowns are the functions g. These equations can be stacked into a matrix equation, and in general, you'll get what's called a generalized vandermonde matrix. Okay, and so if you have repeated roots, instead of having the vandermonde matrix, you will have a generalized vandermonde matrix inverse needed for solution. And so using this method, then we can obtain a to the power k in general. So stay tuned for the worked example problems.